Okay, let me begin. And this is a review of probability. Probability is an important mathematical tool. It models phenomena that have randomness attached to it. In statistics, the phenomena that have randomness attached to it is the selection of the sample. And you will want to then from the sample, make decisions about the population. And because of the randomness, there will be a certain probability that the decisions are correct. The sample space for a random phenomenon is the set of all possible outcomes that can occur. An event is a subset of the outcomes. Any set could be a set containing nothing, the empty set, or it could be all of the outcomes, or it could be a subset. The probability of an event. Suppose your sample space has a finite number of outcomes. Each of those are equally likely. This quite often is the case. Then the probability of the event E occurring is the number of outcomes in E over the total number of outcomes. N brackets A is denoting the number of outcomes in the set A. So this definition of probability, there's more advanced definitions of probability, but this definition of probability applies when there's a finite number of total outcomes and each one of them is equally likely. Some rules for probability. If you have two events, A and B, and A union B is the union of those two events. It's all of the outcomes in A together with all of the outcomes in B. Some of them might be counted twice. They might be in both A and B. P of A union B is P of A plus P of B minus P of A intersection B. If A intersection B is the empty set, P of A intersection B is 0, and that drops out. So then it becomes simple. Probability of A union B is equal to P of A plus P of B. Union means or, A or B. The rule for complements. The probability of a complement is everything that's outside of it. So if you take E and E complement, that'll cover the entire sample space. The probability of E complement is 1 minus P of B. Conditional probability. This is how you have to adjust the probabilities if you know that an event has occurred. So quite often you're given information that the event B has occurred. The conditional probability of the event A given B is P of A intersection B over P of B. You can bring the denominator up to the other side and you get the multiplicative rule for probability. The probability of A given NB is P of A, then times the probability of B given, or you can interchange the A and B. If this is a simple multiplication of P of A times P of B, this is true if A and B are independent. This is actually the definition of independent. It's probability of A intersection B, P of A times P of B. Note that if that's the case, P of A intersection B, P of A given B is just P of A. Counting techniques. The finite uniform probability space. This is when there's a finite number of outcomes and all of them are equally likely. Then the probability of an event is the number of outcomes in E over the total number of outcomes. So in that case, you have to compute P of E by counting the number of outcomes in E over the total number of outcomes. Some techniques for counting. First one is the additive rule. Suppose you have a set of sets, A1, A2, up to, and so on. They're mutually exclusive. That means they don't intersect. They have no events in common. We'll let Ni be the number of outcomes in AI. then the number of outcomes in the union is N1 plus N2 plus N3. So that'd be the additive rule of counting. So there you have the sets A1, A2, A3, A4. They're mutually exclusive. They don't intersect. Any pair of them don't intersect. If I want to count the outcomes in the union, all I do is add up the number of outcomes in each set. Rule 2. Suppose this is, I'll call a multiplicative rule. Suppose you perform 2 operations in sequence to construct a set. N1 is the number of ways the first operation can be performed. N2 is the number of ways the second operation can be performed. Then product N1 times N2 is the number of ways the 2 operations can be performed. You can illustrate this with a tree diagram. So the first branches are the different ways you can perform the first operation. Then the second set of branches are the different ways that you can perform the second operation. So the total number of paths going from the start to the finish is N1 times N2. Example, suppose we have a committee of 10 people. We want to choose a chairman and a vice chairman. How many ways can this be done? Well, we do that by choosing first the chairman, then choosing the vice chairman. The number of ways you can choose the chairman is 10. There's 10 people. Then once that person's been selected, he's eliminated from the choice of a vice chairman. There's 9 ways to choose the vice chairman. So the total number of ways of choosing those 2 people is 10 times N, 10 times 9, 9. Blackjack, you're dealt 2 cards to start off. What's the probability you'll be dealt 21? You can get a 21 2 different ways. You can first get a 10 or a face card, 10 jack, queen or king. And then the second one, you can get a ace. Total number of 10 or face cards is 4 times 4, 16. Total number of ways of picking an ace is 4. So you could either get an ace first, then a face card or a 10, or a face card or a 10 first, then an ace. So I'm just using the additive rule there, and then also the multiplicative rule to calculate individually of choosing an ace, then a face card, or a face card, then an ace. So the total number of ways you can choose 2 cards is 52 times 51. To the first card is 52 possibilities, second card 51. So the probability of getting a 21 on the first 2 cards is 128 over 2652, or 32 divided by 663. The multiplicative rule in counting in general, supposing that instead of 2 operations in sequence, we're going to perform k operations in sequence. N1 is the number of ways the first operation can be performed. Then once it's been performed, N2 is the number of ways the second operation can be performed. Going down, Nk is the number of ways the kth operation can be performed once the first k minus 1 operations have been completed. So the total number of ways of performing the k operations is N1 times N2 down to Nk. Again, this can be illustrated with a tree. N1 is the number of paths for the first operation. Then once that's been performed, N2 is the number of paths for the second operation. Then once that's performed, N3 is the number of paths for the third operation. So the total number of ways of going from the start to the finish is N1 times N2 times N3. Permutations. Permutations are orderings of objects. How many ways can you order n objects? To do this, you have to choose the first object. There's n ways of doing that. Then the second object, you have to eliminate the one that was chosen at the first. So there's n minus one ways of doing that. And then the kth object, it's going to be n minus brackets k minus 1, because k minus 1 objects would have been eliminated. The number of ways of keeping going down, the number of ways of choosing the nth object, there will only be one left. It'll be 1. So the total number of ways you can order an object is the product, n times n minus 1 times n minus 2, down to 3, 2, and 1. That's the product of the first n integers. That's denoted by the symbol n factorial. Example, how many ways can you order the 4 letters A, B, C, and D? The answer is 4 factorial. 4 times 3 times 2 times 1, 24. There are the 24 different orderings. There's first letter, could have been A, could have been B, could have been C, could have been D. So there's 4 ways of choosing the first letter. Then once that's been done, there's 3 ways to choose the second letter. Then once those 2 have been done, there's 2 ways to choose the third letter. And then finally 1 way to choose the fourth. Permutations of size k. K is less than. How many ways can you choose k objects from n objects in a specific order? So we would perform these k operations in sequence. We choose the first object, then the second, then finally the kth object. Number of ways the first object can be selected as n. Then it'll be eliminated, n minus 1 for the second object. And then when we get down to the kth object, we'd have n minus brackets k minus 1, or n minus k plus 1. So it's the total number of ways that this can be done is the product beginning with n and ending with n minus k plus 1. There's actually k terms here in that product. That can be represented in the factorial symbol, n factorial over n minus k factorial. So this number is usually denoted by npk. It's the product of integers starting with n, decreasing by 1. There'll be k factors in that product. That's equal to n factorial over n minus k factorial. Example. Well, before I go on, sometimes people think 0 factorial should be defined to be 0. It's not. 0 factorial is defined to be 1. This makes this formula work. When k equals n, that's n factorial over n minus n factorial. That's the number of ways you can order n objects, which is n factorial. Defining 0 factorial to be 1 makes that formula. How many ways can you choose permutations of size 3 from the 5 letters A, B, C, D, and E? That would be 5p3, 5 factorial over 5 minus 3 factorial. This 2 factorial cancels in with the numerator on the left, 5 times 4 times 3, 60. So there's the 60 permutations of size 3, chosen from 5 objects. An example, suppose we have a committee of 10 people and we want to choose a chairperson, a vice chair, and a treasurer for the committee. So we'll be choosing 3 people. The order of selection is important because the first person chosen will be the chair, second, the vice chair, the third one, treasurer. The solution is 10p3 Again, we're choosing 3 objects from 10, and the order of selection is important. 10 factorial over 7 factorial, 10 times 9 times 8, 720. Here's a question in probability. Suppose you have 10 people, 4 of them are male. No, 6 of them are male, 4 are female. What's the probability if I chose all 3 executives with the same chance? What's the probability that they're all male? So we want to select 3 from 10. A number of ways that can be done is 10 choose 3, 10p3, 10 factorial over 7 factorial, 10 times 9 times 8, 720. Now suppose we want to choose them so that they're all male. Then we'd have to select 3 from the 6 in a specific order. We'd be selecting from the 6 males, that's 6p3, 6 factorial over 3 factorial, 6 times 5 times 420. So the probability of them being all male is 120 over 720, 1/6. Combinations. These are different from permutations. These are different from permutations because the order of selection is irrelevant. A combination of size k from n objects is a subset of size k where the order is irrelevant. Here are 5 objects. I want to choose a combination of size 3. So that would be 3 of those elements. Order of selection is the same combination. There's a total of 10 combinations of size 3. There's the different combinations. In combinations, ordering is irrelevant. Different orderings result in the same combination. In permutations, order is relevant. Different orderings result in a different permutation. How many ways can you choose combination of size k from n up? Suppose n1 is that number. You can then choose a permutation by first selecting combination. There's n1 ways that can be done. And then ordering the elements. There's n k factorial ways that can. So npk, which we know is n factorial over n minus k factorial, is n1. Another way of counting it, it's n1 times k factorial. So then we can solve for n1. n1 is npk divided by k factorial, n minus n factorial over n minus k factorial, k factorial. This is the number of combinations of size k. So that's the formula. That number is denoted by sometimes this nck, number of combinations of size k, or nk with round brackets around. Both of those are read n choose k. You're choosing k objects from n objects. The order of selection is irrelevant. nck is also called, or n choose k, is also called a binomial coefficient. That's because when we expand x plus y to the n, using the binomial theorem, these numbers appear as coefficients for x raised to a power y times y raised to a power. This is the binomial theorem. X plus y raised to the power n is n choose 0, x to the 0, y to the n. N choose 1, x to the 1, y to the n minus 1. down to n choose n, x to the n, y to the 0. Or if we use the other symbol for combinations, n choose 0, n choose 1, n choose 2, down to n choose n. Now the proof of this, you'll get a term x to the k, y to the n minus k if you select x from k of the factors of x plus y to the n, and y from the remaining factors. The number of ways that you can choose k factors that you select n from is n choose k. So you get n choose k terms that are equal to x to the k, y to the n minus k. So when you expand x plus y to the n, you get n choose 0, x to the 0, y to the n, n choose 1, x to the 1, y to the n minus 1. This is the binomial theorem. Pascal's triangle. This is a useful computation. It has ones along the edges. Then the numbers that are in the interior are just the sum of the two numbers that are just above. So the 2 is 1 plus 1. The 3 is 1 plus 2. 4 is 3 plus 1, 6, 3 plus 3. So these numbers in here are just the sum of the two numbers above. These calculate the binomial coefficients. The two edges contain ones. The interior entries are just the sum of the two nearest entries in the rows above. And then the nth row are the binomial coefficients, n choose 0, n choose 1, down to n choose n. So that's 1 choose k, k equals 0, 1. That's 2 choose k, that's 3 choose k, and 4 choose k. And when you expand x plus y to the nth power, the coefficients of the different powers of x and y are in each row. There's the binomial theorem for n equals 1, 2, 3, 4, 5. Those numbers that appear next to the powers of x and powers of y are just the rows in Pascal's triangle. A summary of rules of counting. The additive rule. This is when you have events that don't have any outcomes in common, and I want to calculate the number of outcomes in their union. That'll be the number of outcomes in A1 plus the number of outcomes in A2 plus the number of outcomes in A3. The multiplicative rule. If you perform two operations in sequence, and one is the number of ways the first operation can be performed, and 2, the number of ways the second operation can be performed, then the number of ways the two operations can be performed is the product n1 times n2. That can be extended to performing k operations in sequence. To calculate the total number of ways you can perform k operations, calculate what number of ways the first one can be performed times the number of ways the second one can be performed times the number of ones the k operation can be performed. These are the basic rules of counting. The basic counting formula. These were developed using these rules. Ordering. If you want to order n objects, the way that can be done is n factorial. Permutations. If you want to choose k objects from n objects in a specific order, the number of ways that can be done is npk, n factorial over n minus k factorial. Combinations. If I want to choose k objects from n objects, order of selection irrelevant. That's the difference between permutations and combinations. The number of ways that can be done is n choose k, n factorial over the product k factorial, n minus k factorial. To apply these rules and basic formula The trick is just to break up the counting problem into a subsequence of operations that you're going to perform and use the basic counting plan. I'll apply this to Lotto 640. In Lotto 649, there's 49 integers, 1 to 49. The Lottery Corporation chooses 6 winning numbers, so there's 6 winning numbers. And then there's a bonus number, 7th number chosen. If the order of selection doesn't matter. You get the same numbers, but in a different order, that's the same result. Here's the number of ways you can choose the 6 winning numbers. That's 49, choose 6, 49 factorial or 6 factorial times 43 factorial. The 43 factorial can cancel out the numerator, and we're just left 49 down, product down to 44, so on. That's 13,983,860. So when you choose 6 numbers out of the 49, there's 13,983,816 ways that you can do that. This is how you can lose or win. If there's no winning numbers amongst your 6, you lose. If there's 1 winning number, you lose. If there's 2 winning numbers, you lose. When you start to win, if you get 2 winning numbers plus a bonus, you get $5. If you get 3 winning numbers, you win approximately $10. You win $10. 4 winning numbers, you win about $8. It'll depend on how many people picked 4 winning numbers. If you pick 5 winning numbers, you win about $2,500. If you pick 5 winning numbers plus the bonus, you get about $100,000. If you get all 6 winning numbers, you get about $4 million. That could be higher if the prize has been carried over. So let's count the different ways that this can be done. No winning numbers. That means all 6 numbers have to be chosen from the losing number and the bonus. There's 43 losing numbers and 1 bonus. So that's including the bonus. 43 choose 6. That works out to be 6,096,454. To count the number of ways you can get 1 winning number, you have to choose that winning number from the 6 numbers the Lottery Corporation picked. So there's 6 choose 1 way of doing that. And then the 5 have to be chosen from the losing numbers plus the bonus. 43 choose 5. 5,755 times 580. Get 2 winning numbers. I have to choose the 2 winning numbers from the 6 winning numbers. The remaining have to be from the losing number. I can't choose the bonus in that case because it'll go into the next one. There's 1 million possibilities to get that particular outcome. 1,678,950. To get 2 winning numbers and the bonus, you have to choose the 2 from the 6 winning numbers, the 1 from the bonus, and then the remaining 3 have to come from the losing numbers. There's 172,200 ways that can be done. Counting the number of ways you can get 3 winning numbers. So you have to choose 3 numbers from the 6 numbers the Lottery Corporation says are winning numbers. And then the remaining 3 have to come from the losing numbers together with the bonus. 246,820 ways that can. If you counting number of ways, you can get 4 winning numbers. You have to choose the 4 from the 6 winning numbers, and then the remaining 2 have to come from the losing plus the bonus. 5 winning numbers, no bonus. So the 5 have to come from winning numbers, the times number of ways you can choose the 1 losing number. It can't include the bonus because that would put it into the next prize. 252 ways that can be done. Number of ways you can choose 5 winning numbers plus a bonus. 6 choose 5 is the number of ways you can choose the 5 winning numbers. And then you have to choose the bonus number from the 1 bonus number. 6 winning numbers, there's where you win about $4 million. All 6 numbers have to be chosen from the 6 winning numbers that the Lottery Corporation identified. There's only one way. So here is a table of the different possibilities for 0 winning numbers, 1 winning number, 2 winning number. Each one of those you get no chance of, you get no prize. Then if you get 2 winning plus the bonus, there's the number of ways that can be done. You win $5, 3 winning, you win $10, 4 winning, you win approximately $80. 5 winning numbers, you win about $2,500. 5 plus a bonus, you win about 100,000. And then if you pick all 6 winning numbers, you win $4 million. There's the probabilities of those events. Those are just the number of ways that it can happen over the total number of ways. Notice that to lose, there's a 43% plus a 41% plus a 12%. That would be 84 plus 12, about a 96% chance that you won't win anything. So there's the rules for counting. There's the multiplicative rules. There's the basic counting formula. Orderings, permutations, combinations. The trick to any counting problem is to use the basic rules together with the basic counting formula. Another example, counting poker hands. Poker hand consists of 5 cards, chosen from 52 cards. The total number of poker hands, different poker hands, is 52 to choose 5. The order of selection doesn't matter, so there's no, it's not a permutation, it's a combination. 52 choose 5, which is about 2.5 million. These are the different types of poker hands. The nothing hand. They're not in a sequence. They're not all the same suit. They're different. That's the lowest hand. Next lowest hand is a pair where 2 have the same denomination. The remaining 3 are different denominations. Then you can have 2 pair, 2 that are the same denomination, another 2 that are same denomination, and then a 5th card. You can have 3 of a kind. The next highest hand is a straight. it is 5 cards that are in sequence. If the starting card is X, the other cards are X plus 1, X plus 2, X plus 3, and X plus 4. And they're not all the same suit. Another one is a flush, where they're different denominations, but they're all the same suit. Next highest hand is a full house, where you have 3 denomination X, 2 and a pair. So I have 3 of a kind and 2 in a pair. The next highest hand is 4 of a kind. The next highest hand is a straight flush. They're in sequence going from smallest to largest, and they're all the same suit. We'll exclude starting with a 10 going up to an ace. If that's the case, that's a royal flush. That's the highest hand. Now I'm going to go through and count the number of different types of hands. A pair. A pair can be constructed by choosing the value of X. So X is coming from 13 denominations. And then you select the suits for X. There's 2 values of X, you have to choose 2 of the 4 suits. Then you have to choose the 3 remaining cards. None of those can be X, so X is eliminated. There's 12, choose 3 ways you can choose Y, Z. Then you have to select the suits for Y, Z. There's 4 ways you can do it for each of the 3 cards. So if I multiply those together, those are the total number of hands that would be a pair. The next smallest hand is 2 pair. So there you have to choose X and Y. The order of selection doesn't matter. One of them will be repeated twice, the other one will be repeated twice. So the number of ways I can choose X and Y, that's a combination because the order doesn't matter. Both of them will be repeated twice. And then I have to select suits for X, or choose 2 ways that it can be done, and choose the 2 suits for the denomination Y, or choose 2. Then I have to choose Z. So I can't choose X and Y. So there's 11 choices remaining for Z. 11, choose 1. And then I have to choose its suit. There's 4 possibilities. So the total number of hands of this type would be the product, 78 times 36 times 11 times 4. 3 of a kind. I have to choose X. 13, choose X. I then have to choose the 3 suits for X. 4, choose 3 is the number of ways I can do that. There's actually 4 ways I can choose 3 suits. Another way of looking at that, you have to choose a suit that's missing. There's 4 ways that can be chosen. Choose the denominations Y and Z. So I can't choose the value I chose for X. There's 12 denominations left, 12, choose 2. And then I have to choose the suits for those 2 cards, 4 times 4. So the total number of hands of this type is just a product of those. 13 times 4 times 66 times 16. Full house. I have to choose X, then Y. So that's a permutation, because the order of selection is important. The first one will repeat it 3 times, the second one twice. There's the number of ways I can choose X and Y in a specific order. Select the suits for X. There have to be 3 selected out of 4. select the suits for Y. There has to be 2 out of the 4. Product is the total number of hands. 4 of a kind. I have to choose X, and then I have to choose the 4 suits. There's only one way that can be done. I have to choose the 4 suits that are available. Choose the value for Y. Can't choose X, so there's 12 remaining denominations. Then I have to choose the suits for Y. There's 4 ways that can be. So total number of hands of this type is the product. 13 times 1 times 12 times 4, 620. A royal flush. All I have to do is choose the suit. There's 4 ways that can be done. And then the denomination has to be 10, Jack, Queen. A straight flush. I have to choose the starting value. Starting value can be ace up to 9 possibilities. If the starting value is 10, then it's a royal flush. Then I have to choose the 1 suit. It has to be a suit for all 5 cards. 36 ways this can be done. Doing a straight. I have to choose the starting value. It could be ace up to 10. Then I have to choose the suits. Trouble is I've included in that calculation a royal flush and a straight flush, so I have to subtract off the number that they take up to get the total number of hands of this type. A flush. They have to be all the same suit. There's 4 choices for the suit. Then I have to choose the values X, Y, Z, U, and V. 13, I have to choose 5 denominations out of 13. Again, this will count in that calculation the number of straight flushes and raw flushes, so those have to be removed. So there is the number of hands that are of a different type. The way that I get a nothing hand is I've computed pair down to a raw flush, and I've computed the total number of hands of 5 cards. That's here. So the nothing hand would be, I have to subtract from this the ones that are not nothing. There's the probability of getting the different hands. That'll be the frequency over the total. Maybe we'll stop at this point and I'll ask if there's any questions.
Is there going to be a lab session today?
No, not today. Okay, I think the next time, in the next lab, I'll give a lab session and I'll tell you how to do the next computer assignment.
When will the next lab session be?
The next lab session will be a week from today at 3:30.
So does that mean all the labs are only going to be every second week instead of every week?
Yeah, they will be. They won't be every week. They will. I think I will. If people are having problems with the practice assignment for the next test, they can ask questions during that.
the midterm exam next week on the 1st, are you gonna send the midterm out on Sunday again?
Yeah, I'll do it the same way. Okay,
For this is from last class, but for the two-way frequency table, you said that in the case of independence, the distribution across a row is the same for each row. But what is distribution? What do you mean by distribution?
it means that, okay, if you pick a row, you'll get a different frequency in each of the columns. And that will be the same for each row in the case of independence. So those will add up to the total number of cases in the row. And the way the total cases in the row are distributed, it'll be the same. So if in the first column, half of the observations are there, that'll be the same for each row. That's what you'd expect with independence. If there's not independence, you'd expect higher frequencies in some of the rows than in other rows. They would differ from row to row. So for example, in a case where the rows are blood pressure, no, maybe the rows are cholesterol, and the columns are blood pressure. The number of people who have low blood pressure, the proportion of people who have low blood pressure is the same for each cholesterol level in the case of independence. So this is why the formula, the expected frequency in the case of independence is the row total times the column total divided by n. Are there any other questions? Because I'm going to have to end because I have another class next. So I'll end the lecture